Good morning, champs. In the previous video, we introduced the elementary potential flows: uniform flow, source and sink flow, vortex flow, dipole flow, and stagnation point flow. Now, we are ready to combine two of these building blocks. We take a uniform flow and add a source at the origin. This is our first real superposition problem in potential flow, and it leads to a very important concept. A streamline can act as the contour of a body. We consider a two-dimensional potential flow consisting of a uniform flow in the positive x direction and a source of strength E at the origin. From the previous video, we already know the complex potential of the uniform flow. Because Laplace's equation is linear, we can superpose both flows. Now, we extract the velocity potential and the stream function. Since f of z equals phi plus I psi, we simply add the real parts and the imaginary parts. For the uniform flow, the potential is UR cosine theta, and the stream function is UR sine theta. For the source flow, the potential is E over 2 pi times natural log of R, and the stream function is E over 2 pi times theta. So the full potential is phi of r theta equals UR cosine theta plus E over 2 pi times natural log R. And the full stream function is psi of r theta equals UR sine theta plus E over 2 pi times theta. This is already a very important result because the stream function tells us the streamlines of the combined flow. Next, we determine the velocity field. In polar coordinates, the radial velocity is the derivative of phi with respect to r, and the tangential velocity is 1 over r times the derivative of phi with respect to theta. So first, the radial velocity. UR equals derivative of phi with respect to r. Differentiating gives UR equals U cosine theta plus E over 2 pi r. Now, the tangential velocity. U theta equals 1 over r times derivative of phi with respect to theta. Differentiating gives U theta equals minus U sine theta. Now, we look for the stagnation point. A stagnation point is a point where the velocity is zero, so both velocity components must vanish. First, set U theta equal to 0. Minus U sine theta equals 0, so sine theta must be 0. That gives theta equals 0 or theta equals pi. Now, check both cases in the radial velocity. If theta equals 0, then cosine theta equals 1. So UR becomes U plus E over 2 pi r. For positive U, positive E, and positive r, this cannot be 0. So theta equals 0 is not the stagnation point. Now, test theta equals pi. Since cosine pi equals minus 1, the radial velocity becomes UR equals minus U plus E over 2 pi r. Set this equal to 0. Minus U plus E over 2 pi r equals 0. Solving for r gives Rs equals E over 2 pi u. So the stagnation point is located at Rs equals E over 2 pi u. Theta s equals pi. In Cartesian coordinates, this is xs equals minus E over 2 pi u. Ys equals 0. Now, we determine the streamline that passes through this stagnation point. This streamline is special because it forms the contour of the Rankine half body. At the stagnation point, theta equals pi and r equals E over 2 pi u. Insert this into the stream function. Psi equals UR sine theta plus E over 2 pi times theta. Since sine pi equals 0, the first term vanishes. So we get psi s equals E over 2 pi times pi, which simplifies to E over 2. So the body contour is given by the streamline, psi equals E over 2. Substituting the full stream function gives UR sine theta plus E over 2 pi times theta equals E over 2. This equation describes the contour of the Rankine half body. By superposing a uniform flow and a source, we create a flow field in which one streamline acts as the boundary of a body. So in this video, we combine two elementary flows, determine the potential and stream function, derive the velocity components, found the stagnation point, and identified the contour streamline of the Rankine half body.